Good morning friends, welcome to the next lecture of this video course on advanced hydrology. In the last class, we started the topic of evaporation in this chapter. We looked at the definition of evaporation, latent heat of vaporization, and then we looked at what are the factors that affect the evaporation in terms of rate of evaporation as well as the total volume. Then we also looked at the other kinds of losses of water from a catchment in the form of transpiration, and the combined term where we combine the evaporation and the transpiration, the total water loss we say is called the evapotranspiration. Then we looked at the concept of what is actual evapotranspiration and the potential evapotranspiration. Then we said that there are all the methods which we can use to estimate the evaporation. They can be classified into three types. All right. First one was the experimental, the second was the empirical, and the third one is analytical. We started looking at the experimental method, in which we use what is called an evaporation pen to estimate the evaporation losses from a lake or a reservoir. We also looked at an example of how much water loss can be there for Indian conditions. We took the example of Hirakud Dam in Odisha. We took some realistic numbers as far as the data is concerned, and then we said we found out that there can be significant amount of losses from evaporation from a reservoir, and it turned out that approximately 200 days out of a year of water supply for the whole state can be lost. And that is where I think we stopped, and what we would like to do today is look at a very important method of estimation of evaporation through analytical methods. All right. So, one of the analytical methods which we are going to discuss in this course is what is called the energy balance method. Okay. So, let me write down analytical methods. Okay. In that we will discuss two methods, as I have said earlier. So, let me first say that one of them is the energy balance method, and the other one we will look at is what is called the aerodynamic. And then there is a third one, of course, in which we will combine these two methods. Okay. All right. So, let us start looking at the energy balance method. In the energy balance method, what we will do is we will apply the continuity and energy equations. As the name suggests, it uses the energy balance. So, it is a combination of continuity equation and then also the energy equation. So, the energy balance method consists of continuity equation and the energy equation. Okay. So, what we will do is to develop the continuity and energy equations applicable for evaporation let us or we will consider an evaporation pan. Okay. All right, or we will consider evaporation pan through which evaporation is taking place. And in the evaporation pan, the evaporation is measured as we all know how, by the rate of fall of water. Okay. Rate of fall of water surface. Okay. So, we will take the evaporation pan. We would look at all the components which we need to consider in developing the continuity and the energy equations, and we will apply the Reynolds transport theorem which we have seen earlier. Okay. So, let us look at the schematic, all right, or the control volume, and then define all the variables. Okay. So, this is a cylindrical evaporation pan, and what we will do is our control volume is right next to the surface or the walls of this pan. Okay, it is on the inside actually. Okay. And then let us say there is this is the water surface elevation or the water in the pan, which is of height h. We will define all these things in a second. The area or the cross sectional area is A, all right. The energy entering is R n. H s is what is called the sensible heat that goes back to the atmosphere, and then there is some heat loss to the ground, G. The density of the water is rho W, and the density of the air or the moist air is rho A here. Okay. And then we say E is equal to negative dH over dt. All right. Okay. So, let us first look at all the basic physical parameters here. Okay. So, you have R n as the net radiation entering the pan, and it is measured, or its units are watts per square meter. So, per unit area. H s is the sensible heat to the air, back to the air, and will not worry about this too much, because we have the sophisticated instruments which should be able to measure these R n and H s, all right. And if not, we will see how to deal with these things later. And then this is important, m v dot is what? It is the vapor flow rate. Okay. M v dot is the vapor flow rate within your control volume or in your pan. Okay. Now, in the pan, the water exists in two different phases, in liquid as well as in the vapor phase. Okay. So, the rate of increase or decrease of your water, all right, species, that is, for liquid it is negative, all right. M v dot is negative for liquid. What do we mean by that? The amount of liquid or the total volume of liquid in the pan is decreasing as a function of time, because water is getting evaporated, right. Okay. And we will take this as positive for gas. This is for liquid and this is for gas or vapor. Okay. So, m v dot is the vapor flow rate. It has a positive value for the water vapor, because it is increasing, all right, as a function of time, and m v dot is negative for liquid. Okay. As per the law of conservation of mass, as we know, the mass cannot be created or destroyed, fine, but it can change its phase all right. So, that is what is happening in this case. Okay. So, that is mv dot, h is the depth of water in the pan, capital G is the heat conducted to the ground or heat loss to the ground. We need to estimate these things somehow. Let us define rho A as the density of air. We have done that earlier. Okay. Rho W as the density of water. Okay. Capital A we have said is the cross sectional area of pan. Okay. For the area, for the case of the lake, it will be the overall surface area of the lake, and then E is the rate of evaporation. Okay. What is the rate of evaporation? It is the rate of water loss from the pan. Okay. This is going to be measured, or we can write in terms of dH by dt, all right, rate of fall of the water surface. All right. Now, if you look at this expression dH by dt, as the time increases, what happens to h? The water surface elevation decreases. All right. So, this quantity is going to be negative, but the evaporation, if we want it to be positive, what we do is we say there is a negative in front. All right. So, the evaporation is nothing but minus of dH by dt. Okay. That is how we are measuring it. Okay. Now, let us first write the continuity equation. Okay. So, this is the control volume we have defined and all the physical parameters in terms of energy and other things. Okay. Now, what we will do for doing this continuity equation is we will consider a steady state process. Okay. Consider a steady state evaporation process. This is important to understand, because the Reynolds transport theorem which we will write, we will have to take the different terms according to this assumption. All right. So, we are considering a steady state evaporation process in which liquid water is first transformed into gaseous state, or I can say vapor, okay, within the CV. This process is taking place within the pan, okay, and then transported out of the CV, all right, that is into the atmosphere, into the atmosphere okay, through a steady state process. Okay. So, let us look at it schematically what is happening. Okay. You have water in the pan, then heat is imparted to it. Okay. It is the heat energy from the sun. Due to that, it is getting converted into vapor, okay, and this process is happening within the control volume or within the pan. All right. So, you have water in the pan receiving heat from the sun, and that heat is getting utilized into converting or transforming the liquid water into the gaseous state. Okay. So, that is one component, and then what is happening to this water vapor? That is getting transported. All right. It is getting transported how? By the wind action. okay, or somehow through a steady state process. All right. Where is it going? It is going to the atmosphere. Remember that this transport of the evaporated water is a steady state process. So, you have the pan, water getting evaporated, and then it is going away, and all of this, the heat is coming in, water gets evaporated, vapor goes away. All right. So, all of this is a steady state process. Okay. All right. So, as you see that in the or within the control volume or in the pan, the liquid is appearing in two phases. It is in the liquid phase as well as the vapor phase, and whenever we have a multi-phase flow, and we have said earlier, we must write the continuity equation for both the phases, right. So, what we are going to say is that the integral continuity equation has to be written separately, that is for liquid and vapor phase of the water, as the CV or the pan contains both phases of water. Okay. All right. So, let us look at this continuity equation one by one. So, first we will take the liquid phase. Okay. I would like to do that quickly. We have seen some of these things earlier. So, we will say that capital B is your extensive property, which is the mass of liquid, in the CV. Beta will be 1 in this case, mass of liquid per unit mass of your liquid. Rho we are going to use is rho of the water, and then dB by dt. Okay. What will this be equal to? All right. Well, this will be mv dot, all right, the rate at which, or the vapor flow rate, or rate at which the liquid is getting reduced in the CV. So, let me put a negative in front. So, it will be negative, because the mv dot itself is negative for liquid we have assumed. So, we need to put a negative in front, so that dB by dt is positive. Okay. All right. So, what will be the Reynolds transport theorem? dB by dt on the left hand side, okay, which is minus of mv dot, is equal to the sum of two components. What are the two components? First one is the time rate of change of extensive property stored within the control volume, that is number 1. Other one is the outflux, net outflux of the extensive property flowing across the control surface. Okay. So, if you write the first one, you have d over dt of over the control volume of your beta is 1, rho is rho w, beta rho dV, plus over the cross section or control surface of your beta is 1, rho v dot dA. So, v dot dA. Okay. And this we say is equation number 3.5.1. All right. Okay. So, what would the first quantity be? All right. It is the time rate of change of extensive property stored within the control volume. All right. What is the extensive property? In this case, the extensive property is the mass of the liquid water. Is the mass of the liquid water changing as a function of time in the pan? Yes, it is. Okay. Although your overall process, evaporation process is steady state, but you see that the amount of liquid is reducing in the evaporation pan, because it is getting converted into vapor. All right. So, as far as the liquid is concerned, that d by dt term will be, as you can see, equal to rho w you can take outside. All right. D by dt of your volume, total volume is A times area A is the cross sectional area and the rate at which it is reducing is dH over dt. Okay. So, if you take the rho w out, you have V over T, all right. So, you have A dH over dt. So, overall if you see these two things, the quantities or the units will be same. So, the first term will be equal to rho w A dH by dt. What about the second term? If you think physically, what does the second term represent? Well, it is the amount of or the outflux of extensive property flowing across the control surface. Okay. Is there any liquid water flowing across the control surface? What are the control surfaces? Well, you have the cylindrical vessel, then there is a bottom which is fixed, all right. No water can flow through the bottom, no water can flow through the pan across it, okay, and no water can, liquid water can flow through the top, okay. It is only the vapor which is flowing upwards, okay. So, as far as the liquid water is concerned, this second term is going to be equal to what? 0, okay. It is very important to understand and see that, but you should be able to see that once you understand what is your extensive property to which you are applying this Reynolds transport theorem. Okay. So, the second term here will be 0 because there is no movement of liquid across any of the control surface. Okay. Okay. So, once we have understood that, then all you have is negative mv dot is equal to rho w A dH over dt. Okay. We have already said what is dH over dt, it is minus E or E is equal to minus dH over dt, right. So, that would mean then your mv dot is equal to rho w A E. Okay. This is your equation number 3.5.2. Okay. So, this is your continuity equation for the liquid phase in the evaporation pan. Okay. Now, let us look at the same thing for the vapor phase. For the vapor phase, the extensive property we will define as the mass of your water vapor in the CV. Okay. What is beta? For the mass of the water vapor in the air, we have seen that already, it is nothing but the specific humidity which we denote as QV. Okay. And then rho is equal to what? It is the moist air, density of the air, and dB over dt is your mv dot, which is positive for the vapor, we have said already. All right. So, when we put all these things in your Reynolds transport theorem, the left hand side is dB over dt, which is mv dot, is equal to, again you have the time rate of change of extensive property stored within the control volume. Okay. You have to remember this expression by heart, it should just come out automatically. All right. So, this is going to be equal to beta is QV, rho is rho A and dV. Okay. QV rho A dV plus over the control surface of your beta rho A and V dot dA. Okay. And let me number this as 3.5.3. Okay. So, all we have done is we have written the Reynolds transport theorem continuity equation for the vapor phase in the evaporation pan, which is your control volume. Okay. Now, which term will be 0? Let us see. Okay. Physically, see the important thing is we have to understand our physical process. Okay. What is actually in the nature we are trying to model, and what are the extensive properties, what is your equations, which term is representing what, and then we should be able to see that. So, let us see first one. First term of this equation 3.5.3 represents what? Physically it is time rate of change of extensive property, that is mass of the vapor. So, time rate of change of the mass of the vapor, all right, within the control volume. Is it changing? No. Why? Because we have said that it is a steady state process. Okay. Remember, the assumption was that the transport of water vapor, all right, is a steady state process. Okay. So, because we have assumed this to be steady state, so the first term on the right hand side is going to be equal to 0, because there is no accumulation of water vapor in your control volume. Okay. All right. So, if we understand that, then all we would have is mv dot we can write as rho w a e, all right, is equal to over the control surface of your q v of your rho a and v dot d a. Okay. So, this is a complete continuity equation. We will number it 3.5.4 and say that this is your complete continuity equation for the evaporation process. Okay, which is very useful for finding the evaporation. Okay, once we can estimate the right hand side. Okay. All right. Now, as we said that we are looking at the energy balance method, all right, and we have assumed the Rn, Hs and G and all those things. So, we need to take care of the energies also. This is as far as the mass balance is concerned. Okay. So, we apply the energy equation, all right, and then we can combine the energy and the continuity equation, that will give you the final expression or formula for estimating or calculating the evaporation. All right. So, let us quickly then look at the energy equation. For the control volume we have just defined. So, let me write quickly that B is the total energy. Okay. So, that is your total energy of the fluid, all right, which is possessed by the fluid. Capital B is the energy per unit mass. Okay. Now, we have defined all those things actually. So, what I will do is first I will write this energy equation which we have written at the beginning of this chapter. Okay. So, I will just go back and write it as the left hand side. We use the first law of thermodynamics. We say is the dB by dt is dH by dt minus dW over dt. Okay. We have defined this from the first law of thermodynamics is equal to d over dt. First term, the same thing, is your accumulation term or the amount of extensive property, the rate of change of that. So, it is q beta is EU plus half of V squared plus GZ. Okay. That was the beta, and then you have the rho and dV. Okay. This is the first term, and the second term is going to be over the control surface of your EU plus half of V square plus GZ. Okay. That is your beta rho V dot dA, all right, and I will say that this is your this whole thing is 356, all right, 356. Okay. All right. So, this 2 actually let me make sure that this is square here. Okay. All right. So, let us look at this equation now term by term. Okay. Which quantity is going to be 0 and which quantity is not going to be 0, and how we can simplify dH by dt and dW by dt terms. Okay. So, let us move on and use our knowledge and say that on the left hand side, what was dH by dt? It is the rate of heat input, all right, or the heat transfer to the system. Okay. What is the system? Our system is this evaporation pan. Okay. So, how much is the heat which is, or the net rate of heat input going into your control volume. Well, in terms of the things we have, it is nothing but Rn goes in minus Hs goes out minus G is the heat loss to the ground. Okay. So, this is the net rate of heat input from the external sources, we have it on the left hand side. What was the dW by dt term? It is the rate of work done, the rate of the work done by the system. Okay. Now, I would just like to spend maybe a minute on this quantity dW by dt. Okay. When we have a pipe network system, for example, where the water is flowing in the pipes or in the channels for that matter. Okay. What we have is, we have what is called a pump. Okay. Whenever you install a pump, what does a pump do? A pump imparts energy to the fluid or to the flowing water. All right. Let us say you do not have enough energy to or enough head to take the water downstream, the gravity head is not available, and we need to take the water to the higher level or the higher ground. What do? We just pump the water. So, we put these artificial energy sources, all right, a pump for example, which will jump the energy and then you can take the water. So, it is that kind of work. So, pump is doing the work on the system. Similarly, we may have a turbine, all right, which will take the energy, all right. On the in the dams, what do we have? We have the turbines on which the water will fall, and that energy gets converted into your first mechanical and then electrical energy, all right. So, these are the kind of work, or these are the kind of elements we are looking at here. So, with that background in mind, is there any source of heat, all right, either the heat being imparted to this system or taken away, other than what we have considered Rn, Hs and G, that will constitute the rate of work done on the system. Obviously, there is no other element of source or sink in terms of the heat in this system. Okay. So, what we will then say is that this dW by dt term is nothing but equal to 0. So, there is no work done on the system, okay, in the natural process of evaporation. All right. Okay. Now, what is V? V is the velocity of water in the evaporation pan, all right, which is actually very slow, extremely slow. So, for practical purposes, we say that it is 0 for water in the evaporation pan. Okay. Also, what is dz over dt? Okay. We are looking at one of the things on the right hand side, the first term actually. Okay. Is the datum head or the datum energy of the overall system changing as a function of time? All right. The evaporation pan is probably put at some altitude, all right. That altitude is not changing, the datum head is not changing as a function of time. So, dz by dt is also equal to 0. Okay. So, it should be very easy to see that dz by dt is also equal to 0. Okay. So, once we put all these things in our equation, which we have just derived, that is this one 3.5.6, all right, then what do we get is dH by dt is equal to your d over dt of triple integral over the control volume of your EU times rho w and dV. If you go back, you see that the first term on the right hand side, the V is 0 and then dz by dt is 0. Okay. So, all you have is the EU term. Okay. So, that is out of the first term, all right. So, that is what I have written, d over dt of over the control volume of EU rho w dV. Okay. What about the second term? Okay. This second term is this one. It is very important to understand this one. Okay. The second term in this equation, physically what it is representing? it is representing, let me write it down or let me first say it. The second term on the Reynolds or in the Reynolds transport theorem is what? Net outflux of extensive property flowing across the control surface. Physically that is what it is. Okay. And what is the extensive property in this case? The extensive property is the heat energy or the total energy. All right. So, what does the second term represent then? It is the net outflux of heat energy flowing across the control surface with the flowing fluid. Okay. Let me write it down and then we will see what it is. Okay. The second term on the RHS of let me see the equation number, which is 356. Let me go back, it will be 346, no I am sorry, it is 356, is it? Yes. So, it is 356 is physically it is the net outflux of heat energy, okay, carried across or flowing across the control surface with what? With the flowing water. Okay. What is this equal to? What is the net outflux of the heat energy flowing across or carried across the control surface? All right. We have seen that the energy exchanges are Rn, which is coming in, Hs is the sensible heat out to the atmosphere, we have taken care of that, and also to the ground. There is no heat energy taking place across the pan, nothing across the ground which we have not taken care of, and there is nothing to the atmosphere. Okay. So, with the flowing fluid including vapor and liquid, there is no flux, there is no heat energy which is carried across the control surface. This is very important to understand that. Whatever are the heat energy exchanges, we have accounted for them. Net heat comes in, that is used up in converting the liquid water to the vapor. All right. So, that is all there is to it. So, we will say that this is equal to 0. Okay. It is very important to understand. So, I am going to say that this whole quantity is equal to 0. Okay. So, the second term on the right hand side of your energy equation applied to this case is equal to 0. Okay. Please see that on your own if it is not clear. Okay. Try to think about it. Okay. So, once we have that, then I come to this equation, this one, the second term is 0. All right. So, that is all I will have. Okay. And this I am going to number as 3.5.7. Okay. Now, in this equation 3.5.7 which we have written, this one, that is, if we assume, what does this represent basically? The right hand side represents the time rate of change of internal energy stored within the control volume. Now, out of the total energy, the datum head and the kinetic energy, those things are taken care of. So, only thing we have is EU, which is the internal energy. All right. So, the total rate of change of the internal energy is what we have to write on the right hand side. Okay. So, if we assume that temperature within the CV is constant. Okay. If we assume that the temperature within the control volume or in the pan is constant, then, which actually is a reasonable assumption, because during the process of evaporation we have seen as the definition of evaporation that the temperature is constant, okay, during evaporation. Okay. So, if we assume the temperature within the pan to be constant, then the only change in the heat energy stored within the pan or the CV is equal to what? Is the change in the internal energy. Total heat is equal to your internal energy, all right, which is in joules per second. Okay. So, it is the time rate of change of internal energy, and we are saying it is joules per second. What will this be equal to? This internal energy is related to what kind of energy in the fluid, in water? Obviously, during evaporation we are talking about the latent heat of vaporization, all right. And if we say that the latent heat of vaporization is denoted by LV, then we can multiply this by m dot V, all right. Now, see that what is LV? The LV is, the units are joules per kg. What is the units of the latent heat of vaporization? It is the energy per unit mass of the substance. So, it is joules per kg. If we multiply this by mv dot, and what are the units of mv dot? It is kilograms per second. It is the mass or the vapor flow rate, right. So, it is the kilograms per second. So, you see that LV multiplied by mv dot will be nothing but joules per second, all right. So, that is what we want here. Okay. Okay. So, if we use this equation, and let me see that this Rn minus Hs minus G is your dH by dt. So, you are going to put this in this equation here, and this whole thing, the d over dt of triple integral of EU rho w dV is LV mv dot. So, let me go to the next page and then say that basically you have Rn minus Hs minus G is equal to LV mv dot, and let us say this is 358, all right. But what is mv dot? Well, mv dot we have already said from the continuity equation as rho w a e, okay. And this I am going to say for simplicity as rho w e, and if you assume a is equal to 1. If you are you want to define the evaporation per unit square area, then you can take a is equal to 1, and then we will have the evaporation from unit area. Okay, so, we put all these things into 3.5.8. What we are going to get is then E is equal to 1 over LV rho w times Rn minus Hs minus G. I am sure that this equation sounds quite familiar to many of you. Okay. This is nothing but the energy equation you may have studied in your undergraduate classes. Okay. So, this is your energy equation we have derived from the Reynolds transport theorem, in which we have taken the movement of the fluid, we have written the continuity equation for the liquid phase and for the gaseous phase, then we have written the energy equation and we have combined those two and finally come up with this expression. Okay. So, let me say that this is 3.5.9. Okay. This is the final energy balance equation for evaporation. Okay. Now, you see that this final expression for evaporation involves three things as far as the energy is concerned: Rn, Hs and G. Normally, the incident radiation or the incident heat energy Rn we can measure using the instruments. In fact, most of the meteorological stations will measure the heat coming in. Okay. So, Rn is something which can be easily measured. Okay. However, there are practical difficulties in estimating or measuring the Hs and G. All right. But the good thing is that their fraction or the amount of Hs and G as compared to the total heat coming in is very small. All right. So, as engineers or practical people, what do we do? Anything that is small, all right, as compared to an other quantity, let us say for example, Rn is 100 and this is 0.1 and 0.2, we can neglect it. Okay. So, you say that if Hs and G we can neglect or they are close to 0, then your final expression, or the we will call it ER, rate of evaporation due to your energy methods, is going to be equal to Rn over Lv rho W. Okay. This is the very small little sweet formula I am sure you may have seen in your earlier classes. Okay. So, this is the energy balance method for estimating rate of evaporation, all right, in which the physical factors we have considered is mainly the heat energy. Now, the second method, as I said, we are going to consider is what is called the aerodynamic method. Aerodynamic method, okay, in which we will consider the expression, derivation of expression for evaporation, which considers not the heat energy we have already considered in the energy balance method, but two other main factors, all right, which is the humidity and the wind velocity, all right. But before I go to the aerodynamic method, all right, what I would like to do is I would like to look at some empirical equations, all right, which can be derived from this aerodynamic method. The final equation of the aerodynamic method, which we will find, it is the mother of all the empirical evaporation equations, all right. So, let me just say that it will consider humidity gradient or deficit rather, and wind velocity, okay, all right. And we will develop this equation, but first let us look at a couple of empirical equations which are based on this equation. I am doing this intentionally because you may have seen these equations, and then once we derive the aerodynamic method, you will be able to see that that is the most general one, and how we can derive the other equations out of this empirical equation. Okay. So, the first one of the empirical equation which we are going to see is the Myers formula. It was developed by Meyer in 1915. Okay. And if you remember, it gives you the rate of evaporation by this expression. Okay, where k is some constant. All right, let me first define the quantities, okay, then I will come back to this expression. So, what is U9 is the monthly mean wind velocity in kilometers per hour. Okay, it is the wind velocity where at 9 meters above the ground level, okay, and Km is your coefficient accounting for other factors, okay, that is your size of the lake, etc. Okay, and this is given as 0.36 approximately for large and deep waters or lakes, and its value is about 0.5 for small and shallow waters. Okay. What is EW? In this equation, EW is the saturated vapor pressure. Saturated vapor pressure at the water surface or close to the water surface, okay, which will depend upon the temperature, and we have seen its expression already. Okay. And EA is the actual vapor pressure corresponding to the relative humidity at that point of time. Vapor pressure of overlying air at a specified height okay, and both of these things, these pressures are in millimeters of mercury. Okay. Pressure this we have seen that can be measured in pascals as well as in the as a barometric units and the millimeters of mercury. Okay. In this particular equation, because it is empirical equation, it involves these coefficients, the pressure has to be, the vapor pressure and the saturation vapor pressures have to be substituted in millimeters of mercury. Okay. And once we have the value in pascal, we can always convert it into any other units. All right. So, this is the formula in which if you see that the rate of evaporation E L or the monthly rate of evaporation E L is a function of two things. It is taking care of two physical factors. One is the deficit. What is it? E W minus E A. What is E W minus E A? It is the difference in the saturation vapor pressure and the actual vapor pressure. All right. So, it is the deficit. All right. Higher the E A, lower will be the rate of evaporation. All right. Lower the value of E A, higher will be the evaporation, and we have seen that earlier. Okay. And the second expression or the second factor, physical factor, which this method is accounting for, is the wind velocity. All right, because wind velocity is what is responsible for removing the evaporated water from the lake. Okay. So, it will depend upon the wind velocity also. So, you see that the Myers formula is accounting for the vapor pressure deficit and the wind velocity, and our aerodynamic method also takes care of these two things, but it has been derived from that aerodynamic method. We will look at that little later. Okay. So, that was number 1 or the first empirical equation, and the second one you may have seen is what is called Rohwer's formula for estimating evaporation, and this was proposed by this particular gentleman in 1931. Okay. What it does is it considers atmospheric pressure, all right, also. Okay. So, Rohwer's formula, what does it do? It not only considers the vapor pressure deficit and the wind velocity, those two are there, plus it also accounts for the atmospheric pressure for the given climatic conditions. Okay. And then there is a long expression, I am going to write it. So, please bear with me with that. E L is equal to 0.771 times 1.465 minus 3 zeros and 732 times P A, okay, bracket close, and then you have 0.44 plus 0.0733 U naught, and all of this is multiplied by E W minus E A. Okay. We see that 0.77 multiplied by this whole thing multiplied by this, and then this is multiplied by that. Okay. Here your P A is the mean barometric reading at the location. Again in millimeters of mercury. You see that these empirical equations are designed in such a way that they are very easy to use. All right. So, you can have a barometer, it will give you a reading of pressure in millimeters of mercury, you can directly use it in this equation. Okay. So, that is the purpose, and then U 0 in this equation is the mean wind velocity in kilometers per hour at the ground level, okay, which is actually taken at 0.6 meter above GL, okay, right at the ground level. Due to the boundary layer effects, that the wind velocity is actually 0. So, you take it about 0.6 meters above the ground level, okay. That is where most of the meteorological stations may put their anemometer. Okay. So, you see that all other things I am not defining here. So, P A is the pressure and U is the wind velocity, and E W E minus E A is your saturation vapor pressure and the actual vapor pressure. So, this is another empirical equation in which this U 0 appears. Now, one thing I would like to just point out here is that both of these equations use the wind velocity. One is using at the ground, other is using at 9 meters. Sometimes you may have a meteorological station which measures the wind velocity at 10 meters or 5 meters or some other. So, we need a mechanism in which we can convert these velocities at any height. Okay. So, I am going to give you what is called a 1/7 power law. Okay. It gives the wind velocity at any height h, all right, as a function of wind velocity at height 1, which is a constant actually in this equation C, times h to the power 1/7. Okay. This is actually called the 1/7 power law. Okay. So, if you have the wind velocity at any height, you can find out its value at any other height. For example, you have let us say u 2 over u 1, you can apply this equation at two heights 2 and 1. So, you have u 2 over u 1 is equal to h 2 over h 1 to the power 1/7, and that will actually give you your u at 2 is equal to u at 1 times h 2 over h 1 raised to the power 1/7. Okay. So, you can use this 1/7 power law to find out the wind velocity at any desired height. Okay. So, I think I would like to stop at this point of time, and just to summarize, we have seen the energy balance method today, in which we derived the expression for the rate of evaporation using continuity and energy equations. Okay. Then we moved on to the aerodynamic method, which we have actually not looked at. We will do it in the next class, but we have seen a couple of empirical equations which are based on this aerodynamic method. So, what I would like to do in the next class is look at this aerodynamic method.